I want to start today's video by quickly going over the last problem that we got to in class today. And you had to find the total amount of snow that falls during this storm. We already discussed it and we briefly went over how to get the answer. But just for the record, this is pretty much the area for the triangle. 1.2 inches. Remember that the area of a triangle is 1/2 base times height. So 1/2 times 2 hours times 1.2 inches per hour. So that's the height. Area for this rectangle is base times height. So 3 hours times the height of 1.2 inches per hour. And then we have another triangle. 1/2 times base times height. So 1/2 times 2.5 hours times 1.2 inches per hour. And notice that we have 2 hours and a half. That's why I put 2.5 hours. So we pretty much add these and we get that the total snowfall is 6.3 inches. So the answer is in inches. And the main discussion or the main reason, the main purpose for today's discussion in class is I want you guys to understand that when we first started solving these problems in class today, we were using distance equals rate times the time. And now I am going to relate the area underneath the function or the curve to get the same amount that we would have gotten using distance equals rate times time. And actually we can take it even a step further. So we have 6.1, estimating with finite sums. So we can approximate the area between the graph of a function and the x-axis by dividing the area into rectangles. So copy this down and then I will show you guys some examples. The key word here is we are going to approximate the area. Okay, approximate the area. So what exactly does this mean? So I'm going to start off with what we call the Wright-Riemann sum. Let's say we have this function, okay? It's not a nice solid constant like we dealt in class today. This is a curve, obviously. And we are talking about the area between A and B. Well, back in geometry, you guys did not learn any formulas for the area under this funky looking shape. Okay, kind of looks like a rectangle or a square, but the top is curved. Okay, so how are we going to determine the area? Well, we can start off by approximating. Remember, the keyword was approximating. And I'm going to show you guys how to approximate using the Wright-Riemann sum. Okay, this is called the Wright-Riemann sum because we are going to create rectangles. Okay, let's say I'm just going to randomly start creating some rectangles here. Oh, let's make that a little better. So just picture drawing rectangles underneath the curve, underneath this region for the curve. Okay, so we have something that looks like this. So these are rectangles. I know they're not the best rectangles, but we have rectangles. The reason why it's called the Wright-Riemann sum is because if you notice, I made these rectangles where the right top endpoint, lands on the curve. Okay, So that's very, very important. So I just happened to make 5 rectangles here. Okay, it just kind of happened. I could have made wider rectangles and less would have fit. I could have made really thin rectangles and more rectangles would have fit. But it just happened that I got 5 rectangles here. Okay, so I'm going to call this, obviously this is the x-axis, this is the y, or f of x, y-axis. So I'm going to call this x1, x2, x3, x4. Okay, so let's look at this first rectangle. Okay, I can actually find the area of this first rectangle by using area equals base times height. Okay, so the thing is that here I have a height of, well, if I label this x1, well then my height goes up to f of x1. Okay, this second rectangle has a height of f of x2. This one is f of x sub 3, and so on. Okay, but let me go back to this f of x sub 1. So we have a height of f of x sub 1, and we have a base of, remember that this is called delta x. So the change here is x. So between a and x1, we have delta x, a change of x. We actually have delta x on all of these here. That's delta x, that's delta x, and so on. Okay? Okay, so given these 5 rectangles that I have here, I'm going to start off by approximating the area using what I just said. Well, if I have a base of delta x and the height of f of x sub 1, then I have area is approximately, let me change that to approximately, f of x sub 1 times delta x. Okay, remember, base times height or height times base, same thing, or it doesn't matter when you're multiplying. That is times there, not a comma, or I'm sorry, not a period, it's times. And then I'm going to add the second rectangle, which is f of x sub 2 times delta x. Then you would do f of x sub 3 times delta x, f of x sub 4 times delta x. So we're going to add that, but remember that it just coincidentally, there was no purpose to me having 5 here, 5 rectangles. So technically, we can do as many as we want, so we can put this dot plus f of x sub n times delta x. So this in turn, or this is the same as the summation of I equals 1 to n of f of x sub I delta x. Okay, so pretty much this is the height, this is the base of these rectangles. The summation, this symbol is the summation. This indicates that we're adding up all of these rectangles. Okay, notice that I have x sub I because that's, I mean, that can be 5, it could be 10, it could be any amount. Okay, so we're starting from I is equal to 1 all the way to the n numbers of subintervals. N is the number of the subintervals. Okay, and that's pretty much everything you need to know about the right Riemann sum. there is a such thing as left Riemann sums, and if you notice, I already drew the first rectangle. Notice that the rectangles kind of go up until the left endpoint touches the function. So, makes sense. This is now the left endpoints. So we draw rectangles where the left endpoints touch the graph. Notice this time only 4 rectangles fit here. That really doesn't matter because we can put, depending on how wide we make these rectangles, we can put more or less. So then this will be, so we have x sub 1, this is x sub 2, x3. Now notice that in my first rectangle I need x sub 0, so a is pretty much the same as x sub 0. I need to take that into account because I need to find, that's where the height, that's how I'm going to find the height of this rectangle here. Okay? And this is still delta x. The base is still delta x for all of these. Okay? So the area in turn comes out to be approximately, now the height for the first rectangle is f of x sub 0 times delta x plus f of x sub 1. So the second rectangle here now has a height of f of x sub 1 times delta x. And once again, we don't necessarily have to have 4 rectangles, so plus dot 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 plus f of x sub n minus 1 times delta x. Okay, this n minus 1 tells us that it has to be the left endpoint. Okay, so this is the same as the summation of I equals 0 all the way to n minus 1. Remember, this is what indicates that this is a left sum, not a right sum, f of x sub I times delta x. And that's pretty much what you need to know about the left Riemann sum. One thing that I want you to notice is that given this random blue graph that I drew, notice that it's decreasing. The left sum ended up being an over approximation. Notice that these rectangles have little spots that you counted area that is not underneath the region of the curve that we want. Okay, and same thing with the right Riemann sum. Well, kind of the same thing, but the opposite. Again, this function is decreasing, and this time the right sum was an under approximation. Okay, it gave us, it didn't include some of the area that we need to include for this region. So I want you guys to copy this down. Something to know, if f of x is monotonically increasing, then the left sum will be an underestimate and the right sum will be an overestimate. If f of x is monotonically decreasing, then the left sum will be an overestimate and the right sum will be an underestimate. So copy this down, make sure you know this. It'll save you a lot of time. If you know this, you can use this on the AP test or use this concept on the AP test. I wanted to go over an example with you guys, this one, but I guess I'm going to have to save it for class. And notice that on the interval from 0 to 2, this is increasing, so it's going to switch the concept of the overestimate and the underestimate. And that is it.